Hello and welcome. In this video, we're going to dive deep into an essential concept in electrical engineering to port networks and their impedance parameter, commonly known as X parameters, where you are a student trying to understand circuit theory or a hobbyist waiting to dig into the foundation of electronical systems. This topic will equip you with tools to analyze and simplify complex circuit efficiently.
Let's start from the very basics. A port in electrical engineering is defined as a pair of terminals through which current enters and exits. The key point is that the current entering one terminal must be equal in magnitude and opposite in direction to the current leaving the other terminal. This ensures the port satisfies the current continuity condition, which is essential for proper analysis. A two-port network, as the name suggests, is a circuit or a device with two pair of terminals, one pair for input and one pair for output. These terminals are grouped into two ports, port 1 and port 2. We denote the voltages at these ports as V1 and V2, and the currents as I1 and I2 respectively. Why are two-port networks important? Well, they allow us to model and analyze components like amplifiers, filters, transmission lines, and many more subsystems without dealing with every single internal element. By focusing only on the input and output behavior, we can treat these networks like black boxes, making our analysis simpler and more efficient, as we can see on this picture.
To analyze these networks, we need to relate the voltage and currents at the two ports. There are several ways to do this we can ask. Impedance parameters or X parameters, admittance are parameters or EA parameters, Y or H parameters, transmission or ABCD parameters, and scattering parameters known as S parameters of us at high frequency. In this video, we're going to focus on X parameters, which are especially as awful when the networks in open circuit, meaning not current flows in the output port during the measurement. This is ideal for modeling low frequency networks.
So what exactly are Z parameters? Z parameters are a set of four constants that describe the relationship between the port voltages and port currents. The general form of the equations is, as you can see on the picture, kind of a matrix that it's V1 and V2 equals C11, C12, C21, C22, that multiplies with I1 and I2. And let's break down each term. Z11 is the output impedance looking into port 1 when port 2 is open circuited. That is I2 equals 0. C12 is a reverse transfer impedance. It tells us how much voltage appears at port 1 due to current at port 2. Again, with port 1 open circuited. C21 is the forward transfer impedance, representing the voltage at port 2 due to current entering port 1. C22 is the output impedance seen at port 2 when port 1 is open circuited. C parameters are measured under open circuit conditions, and they are particularly straightforward to use when working with passive linear networks. Now, two important concepts come into play here: reciprocity and symmetry. A network is reciprocal if the transfer impedances are equal, meaning C12 equals C21. This is common in passive networks without any dependent sources. A network is symmetric if the input and output impedances are equal. That is, C11 equals C22. This implies the network behaves the same when input and output are swapped. To make this more tangible, let's consider an example. Imagine a simple T network made of three resistors R1, R2, and R3. R1 is in series at the input, R3 is in series at the output, and R2 connects in the midpoints between input and output. This forms a classic T configuration. We can calculate C parameters for this network using basic circuit analysis. C11 equals R1 plus R2, C12 equals R2, C21 equals R2, and C22 equals R3 plus R2. Notice how C12 equals C21, that confirms the network is reciprocal. If R1 equals R3, then C11 equals C22, and the network is also symmetric. Now let's use the C parameters to find input and output impedances when a load is connected. For example, the input impedance, as we can see in here, for example, the input impedance with a load CL, the output is C in, that it's the C of the input, equals C11 minus C12 multiplying C21, that's divided into C22 plus CL. This formula shows how the load at the output affects the input characteristics of the network. Similarly, the output impedance with a source impedance ZS at the input is the one we can see in the bottom. That is Z of the output equals C22 minus C12 multiplying C21 divided into C11 plus CS. These formulas are invaluable when matching impedances in systems like amplifiers and filters to ensure maximum power transfer.
X parameters find one application across electric and electronic engineering. In RF systems, for instance, they help model impedance mismatches and reflection coefficients. In amplifier design, they allow engineers to predict how the amplifier will behave when connected to a specific source or load. In audio systems, X parameters can describe how much a speaker's impedance changes across different frequencies, helping in the design of crossovers and equalizers. In control systems, two-port models can represent sensor interfaces of actuators where precise impedance control is required. These parameters are also crucial in the disciplining networks that need to maintain signal integrity, especially in high-speed digital or analog systems. To grab up to port networks and C parameters offer a powerful framework for analyzing and disciplining electrical systems. They less so as log and complex systems through a simple lens focusing only on how energy and signals move in and out of the system. Understanding how to calculate and as X parameters can save you a lot of time in your circuit design process and deepening your understanding of system behavior. Thanks for watching and have I this have you a clear and structured understanding of the topic.